My name is Jason Rowe. I'm an assistant professor here at Bishop's University. And I didn't really know what to expect coming into this, so I just threw some slides down and figured I'd just ramble through them and see what comes out of it. In particular, I'm going to talk about extrasolar planets and how visual art is used immensely to try to get the message of the details I do on the astrophysics side and make it make sense to you. So for instance, I have this nice title slide, and then there's this pretty picture that you see over here. So the first thing you might think is that, well, if we're doing all this cool astronomy stuff, it means I've found worlds that have water and beautiful looking suns and moons, but this is quite far from the truth, actually. And this is the name of a game of going from science to then explaining it to you, but also trying to grab your attention as well. So it's a really delicate balance. When we're dealing with the solar system, it's easy. We have lots of pretty pictures of it. Jupiter, Mercury, and so forth. When I grew up, there were 9 planets, and we found some planets that were around different stars. And then we got rid of Pluto and kicked that out because we changed its definition. And now we know of thousands and thousands of planets. But we don't have pretty pictures like this to be able to explain them to you. Instead, what we do is we can measure something like how big is a planet. And then I can say, well, it's about the same size as Jupiter, so maybe it looks something similar to Jupiter. And that's how I explain it. Most of the measurements that we do are based on observing how bright is a star. And then when a planet, if it's oriented the right way, when it moves in front of the star, will block a little bit of light out. So we use things like animations like this to explain that concept. If here's a tiny little planet moving in front of this big star, and over time, as you watch it, it gets dimmer. It's no different if you go outside and you see a distant light on the horizon, you put your hand in front of it, you block the light that comes from it. Right? We do the exact same concept to discover extrasolar planets. And this is what observations look like, all these little dots down there. And we take that information and then transform it into the picture that's above it. So in this case, we have something that we might say looks like the sun, with something that's maybe the size of Jupiter that's moving in front of it. And back in 2009, we launched a spacecraft that cost about $1 billion called the Kepler mission to go and do it. And I went to go watch this, and the first thing I'll tell you, if you go to Florida, skip Disneyland because it's boring, go watch a rocket launch. It's the coolest thing you'll ever see. So this is what it looks like if you have a good camera and you're nearby. I was pretty far away, so that's the picture I took. And that's not the spacecraft going back up and then crashing into the ground. That's the spacecraft disappearing over the horizon. You can see the booster rockets falling back down to the ground over here. And in the background, there's stars. And we now know that most of these stars actually have planets around them. If you know your nighttime sky, and if it was clear tonight, you could probably go outside, at least early in the morning. You can find a summer triangle, and you can find a field of view that the spacecraft looked at to find lots and lots of planets. And this is what the data looks like when it shows up at my desk. Lots of dots, and it's fuzzy, and it's hazy, and it's really hard to make sense of it. When I look at it, I see a planet. For instance, over here, I see there's a bit of a dip in what measure brightness, and I infer that there's lots and lots of planets. So we put together pretty imagery that says, and this is new knowledge for us, the first generation of humans that know that when you go outside, you pick any random star and you look at it, there's a very, very high probability that that star actually has planets that are in orbit around it. Almost every star that we look at in the Milky Way has planets around it. That means there's more planets in the Milky Way galaxy than there are stars. And that's a big number. And some of them, we characterize how far away from their host star. So we think they're in what's called the so-called habitable zone, where they're not too close to the star that they burn up, and they're not too far away that they're icy cold. So we think, oh, they're in the right zone. It's similar to the Earth. We measure their size based on how much light they block in front of the star. We say, oh, it's Earth-like. And then we say, look, we found a planet that's like the Earth that we think has the same conditions as the Earth. So we put together this really awesome picture that we showed to the press. And the tagline we gave was the first validated Earth-sized planet in the habitable zone of another star. And this was the artistic picture that we worked with the artist to come together to do it. And this was actually a very iterative procedure where this image was generated based on what we think an Earth-like planet might look like if it was in orbit around this particular type of star that we saw. This particular type of star is actually cooler than the sun, puts out most of its light in the infrared instead of the optical. So we did things like asking the artist, well, make the trees more palish orangish or something like that, and make the ocean have a little bit of a different reflection that comes off of it. And that was our sort of back and forth to try to portray a little bit of the physics that we thought to go along to give you a more accurate description. This is another viewpoint from another different artist for the exact same system that we observed, and this was her interpretation. So here's this red star of which this planet was orbiting around. So she gave look almost like fall colors, but this is what we think chlorophyll might be like and how it operates if you have to deal with a lot of infrared radiation coming from a host star. And we have distant mountains which are still reflective in the whitish light and snow, and so all sorts of pretty things. The real problem is when you do that, it makes the front page of the Globe and Mail. You know it's Canadian because there's the caribou, but nonetheless, it makes it right front and center. And it looks like we found a planet that's exactly like Earth around a distant star. But that's incredibly far from the truth. All we've discovered about these planets is how far away from their host star, because we know something about their orbital period, and how big are they. But it doesn't tell us if the planet even has an atmosphere or what the planet is actually made out of. For all we know, these are just big iron balls collecting dust far in the universe, have nothing to do with our big goals of maybe trying to find places that are actually habitable. And so it's the challenge between the scientist and the artist to come up with proper graphics and proper representations to help explain the science that we're doing better to you. Right? And that's an ongoing problem, because I really believe that if we keep pushing this imagery on the front page of the paper, that every couple of weeks we say, we found a new planet exactly like Earth, is that you're going to get bored of it, and when we actually do find it, then you're not going to believe us anymore, because we kind of saturated the story that comes with it. Right? So there's a real danger that we can go over the limit for what we actually present, and sometimes over-represent what we're doing. But nonetheless, we should still be excited about what's happening. I truly believe that in the next 10 years, we have the technology that's being built to be able to get observations of these transiting worlds to discover what their atmospheres are actually made out of. And those observations are going to look fuzzy dots and lines on my screen, but they're going to be enabling us to measure what the atmosphere is made out of, and in particular, maybe to be able to measure the chemistry that's present. So we're here on the Earth. We enjoy lots of oxygen that we breathe in and out, and we have the trees that also take carbon dioxide and breathe it, and we produce a balance back and forth between it. So it's the biology that's present on the Earth that shapes the atmosphere as we see it today. So the goal is that by observing lots of these distant planets that we think are Earth-like, and maybe measure what their atmospheres are made out of, that we can maybe point towards evidence that says there must be biology or life that's present that's driving the observations that we see. The hard part is going to be how do we turn that into I'd say imagery that we can use to explain what we're doing and explain that to the public. And it's going to be hard, because the last thing you want is to have ET plastered on the front page of the newspaper when that actually might be really far from the truth. This is one example that we went through a very iterative process, and I thought this one actually worked really well. We had this distant sort of reddish star again, and we talked to the artist and gave a description to her that said the star we think is kind of spotted, we think it's kind of active, so this was her viewpoint with it. And what we were doing is we were measuring the orbital period of the planet as it goes around the star. And because there were other planets present, it meant that that orbital period was no longer constant, because planets also have gravity and will interact with each other. So the concept that the artist came up with to help explain that was, this is where we observed the planet to be, and this sort of ghosty image is where the planet was expected to be. So there was a difference between where we actually saw it and where we might be able to expect it. And the difference between those two was due to the gravitational interaction of the planets that was present. And from doing these measurements, we were able to measure how massive the planet is and measure something about its density. And we recognize this is something that might be similar to Mars in characteristics. It's super close to its hot world, so we have this sort of cratered, red-looking thing that comes on top of it. So I think it did a really good job of portraying the truth to the audience of what we're actually learning in a really interesting, abstract way that's not just showing observations on the screen. So it's a real challenge going forward. Like I said, I really believe that in the next 10 years, we'll have observations that say maybe we're not alone in the universe. And there's lots of good reasons to get excited about it. But it's going to be a real challenge to both prove that and to be able to explain it to you how we actually did it in the first place. So I'll leave it there, and hopefully I have lots of questions towards the end. Thank you.